Good afternoon, everyone.
Good afternoon.
Good afternoon.
Good afternoon. Good to see you again. Um, well, today it's the last lecture of this block, and I think it's a bit of a special lecture in the sense that we're gonna be departing for a moment out of our Neyman-Pearson paradigm, and we're going to step today into the paradigm of Bayes and Bayesian statistics. So we've been talking, actually everything we've been doing up until this moment has been statistical tests that are grounded in the Neyman-Pearson paradigm, and we've talked about null hypothesis significance testing extensively. And while this as a statistics measure works fairly well, it has some limitations, and as we've been discussing the null hypothesis testing, we've already seen some limitations. So we're going to today dive into Bayesian statistics and broaden our view on statistics, broaden our scope. And at the end of this lecture, I will also show you in the direction of some applications that you could use, some programs that you can use for Bayesian statistics, where you have, for example, alternatives to the tests that we perform in SPSS, but then in a Bayesian fashion. So we'll be going into this today. So before we start, I have three topics that I want to cover. The first is the Bayesian theorem, where we will dive into what Bayesian statistics, what the theorem actually is, and after that we'll go into parameter estimation and finally hypothesis testing within the Bayesian framework. Well, Roeland already did a very good primer on Bayesian statistics. So we'll be expanding on that. We had, for the preparation of this lecture, I asked you to watch the video that I made with the Legos. It once was my voice, but then we had to dub it to English, and then someone else did the audio. But I still have the Legos here, and we'll talk about some Legos. Is there anyone else that can't hear me? I think you can hear me, right? Because I
Yes,
said
we can hear you.
okay, very good. So we'll be covering that. So have you seen the Lego video?
And I don't really know where to find it.
It's on the lecture page in Canvas.
Oh, we can't see the slides.
No, I know you can't see the slides. It's on the lecture page on Canvas. The video of the Legos.
The lecture 19 of today.
Yeah.
I can't find it there though.
Yeah, there's
really?
nothing there. It says readings. There's an article part, but there's no video link.
Okay. Well, in that case, I'm going to show you the video.
Thank you.
Okay. I'll first have to find it. Okay, so let's dive into Bayes. So Roeland discussed this with you, right? The probability of A happening given that B happened. This is the fundamental part of Bayesian statistics, where you can actually the point that we are always making within null hypothesis testing is that we are expressing our belief, our probability of the outcome of some experiment, of some random sample, to be based on the fact that we have some preconceived notion of what the underlying truth is, for that matter. So I've stated this that in the sense that if we assume the null to be true, and referring back to the situation what we had, where we had the binomial distribution where we flipped the coin 10 times. Operationalizing the null to be true meant assuming the parameter of the binomial distribution to be 0.5. And the parameter of the binomial distribution can take on any value between 0 and 1. And it's expressed as theta, and we've discussed this at some point. So what it's actually saying in terms of this the Bayes rule is actually only this part above, namely the probability that that a specific data is true given some hypothesis. That is what you're actually testing within the Neyman Pearson paradigm. And what you sometimes want to know is what is the probability of the hypothesis being true given the data that we found. So the Bayesian approach is essentially flipping this notion around, and it makes sense a little bit in terms of what researchers are saying about their hypothesis in research, right? Because when you formulate your hypothesis and you conduct your experiments, then in the end, people tend to describe the results as my hypothesis is true. So based on all the research I did and the data that I found, I conclude that my hypothesis is true. But in the statistical sense of this, well, you're not saying that your hypothesis is true. No, you're saying, assuming the null to be true, it is very unlikely that I find this data, and therefore I refute the null. But refuting the null does not specifically imply that you accept the alternative hypothesis, and essentially, especially in well, if you do, then what is your alternative hypothesis? And we've talked about this extensively, right? Where in the binomial experiment that we did, where we flipped the coin, I assumed at one point that my alternative hypothesis could be that my I think it was Conrad, the coin. I assumed the probability of landing heads would be 0.25. And I told you already that it's a very arbitrary choice, and that it could have as well have been something else. But there are some pretty fundamental assumptions underlying this. And even when we went into the looking into the power and the post hoc power, and trying to find out what the actual power is based on multiple replications of your research, and finding different effect sizes, then you can hone in on what the actual effect size is. But the notion is still then assuming this hypothesis, assuming this state of the world, what is then the probability of finding this data? So it's always within the Neyman Pearson paradigm that you're defining your probability in terms of some assumption about the state of the world, or the state of your parameters, for that matter. And what the Bayesian statistics is trying to do is trying to flip this around and saying, well, what is the probability of my hypothesis given that I find this data? And well, Roland already discussed with you that you're going into the fundamental difference between the notion of probability within these different paradigms, where the frequentist statistics try to take out of the equation everything that's subjective, whereas the Bayesians they put in some subjectivity in here, and we'll go into this during this lecture. But first, I wanted to try to relate the Bayes rule, because Bayes rule in itself there's mathematically nothing wrong with Bayes rule. There's actually no subjectivity in Bayes rule in that sense. But we're gonna see that the Bayesians and at one point introduce some subjectivity into this equation by substituting some assumptions that we have in here. And before we go into this, I wanted to show you the relation between such a Bayes rule and what we've been doing with the null hypothesis testing. So this one is familiar with you, where we stated the null to be true or the null to be false, and we could decide to reject the null or decide not to reject the null. And within this decision table, we could make two types of errors. The type 1 error by rejecting the null while it's actually true, or by not rejecting the null while it's actually false. So you have two decisions that are wrong, and you have two decisions that can be that are good decisions. You remember this, right? This should be.
Yes.
Yeah, very good. So what we're doing now is we're actually looking into this in a bit of a Bayesian framework, where we're saying that, well, we have the probability of some hypothesis, the probability of hypothesis A, and we can contrast this into the probability of not A. And if we have that kind of information, we can determine what the probability is of not B given A. And we can determine what the probability is of not B. And if you look at this, then this is a bit of the same as we've been seeing for the null hypothesis, right? Because we're actually stating we decide to reject the null as a state. This is not B, so in that sense you can relate that to rejecting the null or the hypothesis. So we're actually looking at the same kind of decision, the same kind of decision scheme here. I formalized this, so this thingy here means not. So where this is the probability of A, this is the probability of not A. And you can imagine that if you have the probability of A and the probability of not A, that together it should be 100%, right? So you could have the probability of A that could be 20%, and the probability then of not A would be 80%. So the total probability of something happening or not happening together is 1. That makes sense, right?
Yes.
Yeah.
Good.
I would say maybe, Sharon, maybe instead of A and B, maybe we can use actual, because A and B, in the case of Bayesian statistics, right? One is the data, one is the hypothesis.
Yeah, so I'll get to that. So we'll make the transition at one point. So I first wanted to make it well, at least abstract in the sense that Bayes rule is defined in this way, to lay down the foundation that this is mathematically correct, and then we'll go to the step of substituting to the hypothesis, because that's a very good point, because that is also the point where the Bayesians are making an inference step in that sense.
But is it in Bayesian statistics, is this table relevant or it's just an attempt to link it to the null hypothesis testing?
It's an for me at this point the link to the null hypothesis to the way the decision. It's not such that I really want to relate it to null hypothesis testing. It's that I want to relate it to the decision scheme that you're making. So in null hypothesis, you're actually deciding to reject or not to reject. And in Bayesian statistics, you're also trying to reject and not reject. But there is a very fundamental difference, because with the null hypothesis testing, we're only looking at that specific null, and we can have a broader scope. But we'll get there during this lecture.
Okay.
Can I ask one quick question?
Go ahead.
Because you were talking about the probabilities, the 20% and the 80%. So in this case, the 20% would be the false positive then, and the 80% would be the actual like correct. If we go back to the table,
yeah,
it's
so
like
so this would be the false positive, because it's a false decision based on this, but it's going to be different with Bayesian statistics, but we'll see that. But for now, for example, you could relate this one to for example the prevalence of corona within the population.
Yes.
For example, so let's say that the real underlying prevalence of corona within the population is like 20%. Then the percentage of not the other side is essentially 80%. So what we're trying to do with the Bayesian statistics is, if this is the 20%, then we want to update our belief in the light of the data. So, for example, I have a test. I can decide on, based on the test, that you actually have corona, or that I decide based on the test that you have corona or not. But I can be wrong. And Roeland went into this point where this top part, the A part and the not A part, was essentially his Bayesian decision tree, where he split it up, where this on top here is actually the base rate, the same base rate as Roeland described. So Roeland said that even if you have a highly sensitive test of about 90%, you always have to view those results in light of the total outcome space. Now we're still doing this, and this holds and this works for Bayesian statistics. So, for example, now let's look at this in terms of this probability. So, if the probability of A or the probability of not A is in total 100%, you could look at this chart and say, well, the probability of A and not A together is 100%. So I could split this up in percentages, right? So you could see this in terms of 0% or 100%. And you could also see the probability of B or the probability of not B being 0% or 100%. So intuitively, you could see, well, if you shift this visually and if this probability of A is smaller than the probability of not A, we could actually see that the percentages within these cells are actually smaller. So mathematically this absolutely holds. The video of the Legos is also in the weekly assignment, but I thought someone posted the link to the Lego video in the chat, right?
Yeah, someone did.
Yeah, so let's see. Let's look at it for a second. Let's see. I want a microphone and Safari. Can you still hear me?
Yes.
Yes.
Very good. So I changed my audio input, so that's why I ask. So we're gonna look at this for a second.
In deze video ga ik proberen de theorie van Bayes uit te leggen.
This is the Dutch one. Do we have the English one? Let's see. I don't want the Dutch one, I want the English one. Videos. No playlists. It's in the supposed to be in the playlist for a week. Well, what week? This one. Week 11.
In this video, I will try to explain Bayes' theorem with the help of Lego. This is not my own idea. I based this on a nice blog by Will Kurt, and you can find the link to his blog in the description of this video. What we want to find out with Bayes' theorem is the probability of A given B. And actually, we better say that we want to know the probability of a certain hypothesis given the data. Now, in frequentist statistics, we are always interested in the probability of data given a certain hypothesis. And in this case, we want to know the opposite. In terms of Lego, imagine that this white brick is the data we found, and the red brick is a hypothesis, and the blue brick is another hypothesis. Then we actually want to know the probability of the red hypothesis when we have found the white data. In other words, if you randomly select a white peg, what is the probability that there is a red space underneath? Intuitively, this is quite simple because you can see that half of the white pegs are on a blue space and the other half on a red space, and therefore the probability that a blue or red hypothesis underlies a white peg equals 0.5. That is half. That is intuitive. However, we would like to calculate it, and we can use Bayes' theorem to do so. For this, we need a few elements. We need the probability of the data given a certain hypothesis, hypothesis 1, the red one, or another hypothesis, the blue one. We also need the probability of data. Well, we are going to calculate it. So if we want to calculate the probability of the data given a certain hypothesis, then we actually need these elements. This hypothesis, the probability of the data given this hypothesis. And we can calculate this probability as follows. This space contains 4 times 6 pegs, so a total of 24 pegs, and therefore the probability equals 2 over 24, or 1 over 12. And that is the probability of the data given the hypothesis. If we want to know the probability of the hypothesis, then we have to consider what the total probability space is. What is possible? In fact, we already know that. This is another hypothesis that we can test, but we are not interested in it because we are only interested in hypothesis 1. The probability of the hypothesis can be calculated as follows. 24 pegs in a space of 36 pegs. 6 times 6 is 24 over 36. And that's the probability of the hypothesis. The probability of the data is the last element we need. I'm going to place it here. The probability of the data equals the probability of the data regardless of the hypothesis. Therefore, the probability of the data equals 4 over 36. Now we have, in fact, everything that we need to calculate the probability of the hypothesis given the data that we have. And we can calculate this probability as follows. 2 over 24 multiplied by 24 over 36 divided by 4 over 36, which is going to equal 0.5. And therefore, the likelihood of this hypothesis given the data equals 0.5. Now, we can do the same for the other hypothesis, hypothesis number 2. It would look
Okay.
like this. We are not
I will stop it there. So, in terms of mathematically being sound, it essentially tries to look at the entire outcome space and determine what part of that outcome space is related to your specific hypothesis. Now, in the video I showed, I was talking about the red hypothesis and the blue hypothesis, but as you've seen within this explanation, the blue hypothesis actually means not red. So in that sense, it's not exactly the same as stating that your alternative hypothesis is some other belief. No, it's just not the belief of the initial hypothesis. So trying to relate this decisions scheme here to the Legos, we're replacing the hypothesis and the A's and the B's with the hypothesis and the data. So to get to the hypothesis given the data, we apply the Bayes rule. We've just seen that applied with Legos. And we can fill in the parts that we just discussed with the Legos into this entire scheme. So where we would say, well, what is the probability of the data essentially on top of here? What's the probability of the data given this hypothesis? What's the probability of the white peg looking at all the red pegs, the red area? And we need the total, the hypothesis, so the probability of this hypothesis given the entire outcome space. So this one is the red area related to the entire area, so it's 24/36. And what we also needed was the probability of the data, and that was essentially the area of the data given or in at least with respect to the entire outcome space that you would have. So in terms of how you calculate this data, the probability of the data part, it's the multiplication of this area with the probability of A plus the probability of the other part with the probability of not A. So the probability of the data given A and the probability of the data given not A, and those all multiply. So in relative to what the outcome space for that specific part is. So that is essentially how it's calculated, and that's mathematically totally sound. But we have a little bit of a problem because Roeland talks about essentially this upper part as being the base rate. Could you explain to me again what Roeland meant with that base rate? Can you explain to me what Roeland meant with the base rate?
Maybe just the probability of the hypothesis being true, like the first decision in the tree.
Something like that, yeah.
It's the prior belief, right? It is before you test and look into the data and look at the probability of your hypothesis being true.
Mm-hmm.
Considering the data, you only look at the hypothesis without looking at the data, right? Isn't that the baseline?
So what you're
base
doing,
rate?
yes. So what you're doing now is making the step into Bayesian thinking in terms of saying that you're looking at your prior belief. But if you look at the Lego parts, if you look at that top part here, on top of here, this one, with the way that this is mathematically sound is the fact that, well, if I do this with Legos and I just count the packs that I have here, I know exactly what the entire outcome space is. So essentially, it's the same notion as, well, it's assuming, essentially also the base rate, it's assuming that that is the state of the world. If we actually exactly know what the state of the world is, what the probable what the entire outcome space is, well, then you could obviously simply calculate it, calculate this. But and when Roeland referred to the base rate, this was also like some state of the world that you that you believe. For example, when I said that the prevalence of corona should be could be 20, and if that really is the case, I could actually exactly calculate what the probability of the hypothesis is given the data. And the point that you mentioned, and that is exactly the transition that within Bayesian statistics is happening, is that we are essentially assuming the base rate, because it's obvious that, well, for a lot of things, I don't know what the base rate is. I have absolutely no idea. So it could be 20% for corona, but I actually didn't look up the number, so I don't know what it is. But I have to start somewhere. So the Bayesians look essentially at this base rate in terms of an hypothesis that you could have, or a notion on your, indeed, as you explained, your prior belief. And essentially said, well, if I have this prior belief and I can calculate the probability of that belief, the probability of the hypothesis, given what I've seen in my data, then I can essentially update my belief. So if we rewrite this function, which is totally legit, we're just putting the probability on the hypothesis outside of the outside and multiplying this by this ratio. Then you're actually can point to this part and say, well, this is my prior belief, of the prevalence of corona, 20%. And this is something that comes out of my data. So the probability of the data given that hypothesis divided by the probability of the data will result in an updated belief given that data. So what we have here is this part we called, or the Bayesians called, the prior, the belief that you have prior to seeing your data. So it's the initial belief in your hypothesis. And you have your updated belief. So that's your posterior belief. It's the degree of belief in your hypothesis after you've incorporated the news that, well, the data is true. And the data is true is relative, right? Because the data is just the data, it's just a sample, and you assume this to be true instead of knowing for sure that it's true, because, well, it's still probabilistic. But you assume that. And the quotient that we have up here, it represents the support for the data that the data provides for your hypothesis. And the step that the Bayesians make here is essentially going from this top formula into this one, where it actually states that the posterior belief is proportional to the likelihood. Well, I switched it over. so this is the ratio, this one, it's this one, and the prior belief is this hypothesis represented by this one. So multiplying your prior belief by your data will get you your posterior belief. And well, looking at these formulas, it's actually a bit clear, right? So it says, well, I believe this, but now I still believe that, but only in light of the data. So that means that what the Bayesians do, and when they do it in a good way, they update their prior belief. So they apply their new belief in the next step, so to speak, of their research. So Bayes is about quantifying your belief. Let's say the common sense expressed in numbers, and you're updating your belief in the light of new evidence. And this one relates to the point that I was making. Yesterday's posteriors are today's priors. So that means that if you run your analysis again, you will update your hypothesis, your belief in your hypothesis by the updated belief. So I first think this, then I see the data, then I update my belief, and then I think something else, then I think this. But then I could still say, in the next step, I could say, well, I now believe my updated belief, so that's this one again, and I see new data. And you can update your belief again and again.
Okay, can I ask a question here?
Sure.
Just for understanding. So if you relate that to the corona example, for example,
Mhm.
if you take it to the corona example, so the prior belief would be that the risk of getting infected with corona is so and so. Then you have the actual corona situation taken place. So you have your data, and then based on that, you update your belief. And that's what's happening right now as well. Like that's why new measures are taken all the time.
Exactly.
So then you update your beliefs, and you update also the probability of the getting infected with corona. Right?
Yes, exactly. That's exactly true. So you're essentially updating your base rate in the light of new evidence. And something that you could also think of is that maybe your base rate is not fixed. That could be the case, right? That your parameter is not something that is fixed. That it's something that can even change over time. Well, that notion in the sense of in the sense of frequentist statistics is unheard of. We don't do that in frequentist statistics. We just say, well, our parameters are fixed, but this updating scheme allows you to even have changes in your parameters, and by updating, you could follow what happens. So the prevalence of corona. Well, of course, it's also influenced by the rules that you set for us as a society. So if we have stricter rules that are applying at this moment, well, that would influence the base rate. So there's fluctuation even there. Good points. So one of the things to take into consideration is that this base rate, this initial belief in your hypothesis, that is something personal, right? I could think that the prevalence of corona is 20%, but you might think that it's something else. And in that sense, and that was the beef that the frequentist had with the Bayesians, is the fact that you could have this very subjective personal prior belief in what you think that the state of the world would be, And the frequentist statisticians wanted to get rid of that. They said, well, no, you can't have this notion of probability that's subjective. No, probability is really based on hard facts, on the facts of if you roll a dice and you have a physical dice that is exactly equal on all sides, then the probability is the result of that notion. So it essentially that kind of thinking is tied in with well, even thoughts about the world not being probabilistic, and at the time when this all played out, that notion really was there in terms of physics, for example, where people thought, well, it's the world is not probabilistic, we're just ignorant. And if we know more about every atom and every space, then we could absolutely predict what the outcome will be in every situation. We're now in the quantum mechanics, and we see that that's not really the case. But the Bayesians, they flip this around. So if we look at the generative model comparison between the frequentists and the Bayesians, then within the frequentists, they essentially say that we have a state of the world, and that dictates the way the data, the results of the data. So in the case of our coin experiment, if I set the state of the world in terms of our theta parameter to be 0.5, then the data that will flow out of that is deterministic in the sense that it's still probabilistic, but we know what the probability distribution is given this specific theta. What the Bayesians say is, well, no, we just look at the data and we determine what the most likely theta is based on that data. So if I would have, I threw 2 times heads from 10 times, 2 out of 10 heads, then what is the most likely state of the world, the most likely value of theta? Do you know?
Can you repeat the question, please?
So I threw 2 out of 10 heads. So what is the most likely theta, the parameter value for the binomial for that numbers of heads that I threw?
0.2?
Yes, exactly. So the Bayesians say, well, you have your data, and we can now determine what the most likely result would be based on that data. And this is, of course, it looks a little bit like what we were doing with the post hoc power, right? Where we said, well, if you have the data, we assume the mu to be at the data level. So it's actually sort of the same. Not really, but it comes close to that way of thinking. Okay. What I wanted to do in this part was relate the Bayesian theorem to our null hypothesis. We've seen that we've made the transition from a sound mathematical formula for calculating updated the probability of an hypothesis being true given the data, based on essentially a sound formula. We've seen that applying this to prior beliefs introduces some subjectivity in your outcome, and what we are going to do now is, based on the coin experiment that we've done in the beginning of this course, try to apply this to actually try to estimate our parameters that we have, and in a Bayesian way to get to see how this would work, but mostly because one of the things that we see you've applied with Roeland, and what you're thinking about when you look at this posterior and likelihood and priors, is that you're thinking about probabilities in terms of being essentially one number on a scale from 1 to 100%. And what the Bayesians are actually doing is applying this same notion, but to a probability out to, let's say, an outcome space, all of the possibilities that are out there. And we'll dive into this one. I've added some nice resources. The first two are by 3 Blue 1 Brown YouTube channel. They make wonderful videos, and they have 2 on Bayes' theorem that are really, really wonderful to watch. And I also put in the link to Wikipedia, because I think it has a good explanation on Bayes. Yeah. Okay, we're starting with the Bayesian parameter estimation. You're still with me?
Yes.
Yeah?
Yeah.
Very good.
Yes.
You can
Yes,
still follow
indeed.
along. Very good, very good. So, the Bayesian parameter estimation. It's all based on this notion. Updating your belief based on your prior convictions and essentially listening to the data. So you update your belief based on the multiplication of your prior belief and the likelihood, which is essentially the data. So what is your belief? Well, in one of the first lectures, when I threw that coin, I at some point arbitrarily assumed my coin to be not fair, and to have a theta, a probability of landing heads, of 25%. And we've seen in those lectures that I plotted the null distribution, the binomial null distribution for the and side by side to my alternative distribution, where the underlying principle of the data-driven, the data driver in a sense, was 0.25, and I plotted the binomial distribution for that specific value of the alternative hypothesis. You remember that?
Yes.
And that was a very arbitrary choice. So, yeah, I just thought, well, 0.25. It could have been anything else. It could have been 0.25643 or even 0.40 or whatever. You could have essentially any suggested theta level. So what the Bayesians do is they actually consider all possible values of theta, and they try to essentially put a distribution on this parameter. So I want to ask you, considering all possible values of theta, being between 0 and 1, and it's a real number, what is your belief in theta? So think back about the coin that I flipped, about Conrad that was out of balance and that I hit with a hammer to make the coin flat again, and then it was beaten up. But when I flipped 2 times head, and I could consider what is the probability of that coin landing heads. And if you consider all the possible levels of theta, then what is your belief about this theta? So what I want you to do is get a piece of paper and draw your belief in the following way. You're going to draw a graph with an x and a y axis, where you have on the x-axis you have the values of theta, being 0 to 1. It can be anything in between, so you're going to draw something like a line or whatever. And on the y-axis you have the likelihood. This is meaning that the higher you are on your y-axis, the more you believe that theta to be possible. Do you understand?
Yes, but what's on the x-axis now?
On the x-axis, it's theta. So
Okay.
your belief in what the probability of landing heads actually is, your theta. So I want you to write that down, and then when you're done, show me to the camera. So you all have to turn on your camera and show me what the drawing that you made. So turn on your camera and show me your drawing, if you're done now. So put it in front of the camera. Yes, I'm seeing one. I'm seeing some normal kind of curvish thingy, and another kind of curvish normal-like thing. Oh, I'm seeing a step-sized thing and one that's more skewed to the right. Okay, so I want to ask someone who drew the bell-shaped curve to explain to me why you think what your reasoning is for that outcome.
Well, if the coin has been made fair again, then the probability is around 0.5.
Mm-hmm.
And it's like this because as it gets closer to 0.5, the likelihood kind of gets more. I don't know.
Yeah, that's you're going in a good direction. And could you show me your drawing?
Yeah.
Okay. So why is it that wide? Because the drawing you showed me is quite it peaks at 0.5 and then it's quite wide and it goes out to the side. So why is it wide? What are your thoughts on that?
Well, because it's not gonna be, because some throws may land on tails and not heads.
That's true. That's true. But one thing you have to consider here, we're not talking about throws. We're talking about the possibilities of theta. So you think that a theta of 0.5 is really likely.
Yeah.
But you're also saying that a theta of 0.6 is really likely.
Yeah, but that's less likely than 5.
Yeah. So
Oh, so yeah, because I'm not 100% sure that it's 0.5.
Very good. Yeah. Very good.
It can also be 0.2, but I think that 0.5 is more likely than 0.2.
Exactly. Very good. So what you're saying is you're quantifying your belief and your uncertainty in terms of your distribution. So is there anyone that had drawn a distribution that was not that wide but was a little bit more peaked? Anyone?
I mean,
No?
I'm a horrible drawer.
Show me.
It looks like a pyramid.
Could you show it to me? And you have to say something because otherwise I'm.
Oh yeah, okay. Nah.
Oh yeah. So you had a quite a steep pyramid, right? So
Yeah.
you're thinking in the same lines as our the previous one, where you had the most likely you think 0.5, and then it's less likely the more it goes to the sides.
Yeah, I was thinking I made my one mistake is that I touched the x-axis at one point, whereas even having 10 times head or 10 times tail, it's still probable. Therefore, nothing is improbable.
Yeah, of course.
Though
Yeah.
it would not
Yeah,
touch.
yeah. So in the sense of the y-axis, we would term it likely. It's unlikely to have such and such a value for theta. But I still want to ask, I also saw someone that drew a graph that was like high at one point, then went down and was flat on the other side. Could you elaborate on that one? Could you show me?
Yeah, that was me. But honestly, I missed at the beginning the introduction point, so I didn't know what exactly we have to draw about. But it was this one.
Yeah.
So I was still assuming, but I guess that you continued in your argumentation on the points. So I was referring to a previous step where it's still unfair. And this was just stating that it's more probable that it's still unfair to the one side than the other.
Yeah. So the drawing that you made was, it was totally flat on one side, then it went up, and then it was flat on the other side. So that what you're saying there is that theta values above 0.5, I think it was above, right? It was not below. Was higher.
Depends how you continue the sentence.
Yeah, that's true. So theta at one side is higher than the other side, but it's flat. So that you're saying that all theta values are equally probable on one side, but they are totally not probable on the other side. So if you draw one which is absolutely zero on one side, then you're assuming that that is absolutely impossible. It's absolutely impossible to have a theta value of 0.49. For example. Yeah. So you could absolutely write that down, and you could even test that. I think it's hard to hold this one, because...
You're still talking about the coin, right?
I'm talking about your distribution of theta. So theta is on the x-axis, so you could have every possible value of theta on your x-axis, and you put the likelihood of that theta on your y-axis. So I'm not talking about the coin, I'm talking about the possibilities of some theta between 0 and 1 being true or not. And in that sense, if you would have a fair coin of 0.5, then a distribution in that sense would look in terms of the binomial distribution in that sense would look almost the same as you would have a theta of 0.49, for example. So those things are hard to exclude in the middle.
Yeah.
Absolutely, in absolute sense. And is there someone that draw a flat line? Totally flat?
I did.
Sorry.
Could you show me yours? The flat line? And say something, because otherwise I won't see it.
Yeah, I can. I don't know if you can see it, but
yes, I can.
I just wasn't exactly sure where the line should be, but I did draw mine flat.
And what is the meaning of your flat line?
That we essentially have no idea if the coin is fair again or not. So I guess every theta would be just as likely.
Yeah.
Because we don't know if it's fair or not. That's what I thought. We assumed that we don't know if the coin is fair or not. So that's why I drew it horizontally.
Very good. This is what you call a flat prior, where you assume the likelihood of all possible values to be equal. And you could think about this for a second, right? Because in terms of the physics of my coin, I would regard this flat prior for our coin toss experiment to not be that probable. But it's my belief, right? But it's in terms of if I would have a theta of 1, exactly 1, that would mean that all my tosses would land heads. And if I would have a theta of exactly 0, it would mean that all my tosses would land tails. And I don't think that is possible. The way I try to hammer it flat again, which if I throw it would be highly unlikely that it always lands head, right?
But is that not a bias that we think it's improbable to have?
You could say that that's a bias, but based on physics, I would say it's improbable because. Well, let's state it differently. For example, if I bend my coin and I bend it beyond 45 degrees, and I would throw it, and because it's a round coin, if it would land like this, it would flip around because it's round, right? So in that case, you could state that if it's bent so much like that, it's a theta of 1 would be could be assumed, right? And then you could even state, well, I think it's only 1 and nothing else, because if you flip it and it lands like this, it turns around, so it's always going to be 1. So you could. This is the way that you have to think about drawing such a distribution. But it's absolutely okay to choose a flat prior, but it's the thinking process on what is likely seen in a sense where you're not just restricting yourself to one parameter value, but you're considering the entire space. And this is exactly the reasoning, the thing that the Bayesians do. So this is very good by all of you, whatever graph you've drawn. So let's go back to the slides. So what you've drawn is your prior distribution, your prior belief in your hypothesis. Are you seeing the difference with your null hypothesis testing? You're now considering, as from a Bayesian framework, from a Bayesian point of view, you're not just considering one possible parameter value. No, you're thinking in terms of entire outcome space. You're drawing your belief out. And one of the things that I asked was from you, is there someone that had a more peaked distribution? And because this is something to consider also, right? If you draw a wide distribution around all the theta values, that means, and that one of you stated this earlier, is that you're unsure. Where if you would draw a more peaked distribution, then you would be more sure. You would have more confidence because you assume the likelihood of theta values outside of this range to be lower. Is there someone that drew an inverse parabola? No? Because if you assume your coin to be unfair, you could, of course, think that it's less likely that you have values, theta values around 0.5, and it's much more likely to have theta values that are more on one side, higher on one side, right? That's possible too.
It's possible, but I think it's more probable that it would be one-sided if it's unfair.
Yeah, of course. But if you don't know to what side it would be skewed, then it would be fair for you to think, well, my prior belief is that the probability of these going up on both sides, one or the other, is at least more probable than being 0.5. And then on the light of your data, you could update your belief, of course.
Yeah, it makes sense. It makes sense to be like that, and then towards the 0 and the 1 should again be lower.
Exactly, because like that would be unlikely. Yeah, exactly. And this is the reasoning that you do based on this. Okay, we're gonna have a break because I need coffee again. We're gonna continue 1:15, and we're fresh to continue on this topic then. Yes, very good.
Yes.
See you in a bit. Okay, welcome back everyone. Now before we continue, students.
Absolutely.
Very good. Okay, here we go. So, we've talked about our prior, and we've drawn our prior, and one thing, of course, is that we don't actually draw priors. I think we could, but in mathematical sense, it makes a bit more sense to choose some priors that are, let's say, more mathematical in terms. So what I've done here is I've created a few 4 priors based on a uniform distribution. So one that was mentioned, a flat non-informative prior. I've created one that's a beta distribution and a binomial distribution. So we're going to look at these priors. So they look a bit like this. Indeed, having a flat prior means that you deem every possible value of theta to be possible, to be likely. Whereas if you create a prior or think of your hypothesis in this way, top right, then it means that you think that the 0.25 is highly likely, and you have a bit of a spread around it, but the rest you think it's non-existent, non-possible. You could even have, well, that same notion, but be less confident about this. So you could make it quite broader. Or in this last one, I've thought, well, having the coin being fair is most likely, but I'm fairly I'm not confident about it. So I deem everything to be quite possible in that sense. So what I'm going to do is I'm going to choose a specific prior, and I'm going to be stubborn. I'm going to stick to my initial stubborn belief that I thought my the probability of heads for this specific coin was actually 0.25, and so I'm going to choose the top right prior here, and this top right prior, that's something to consider for a moment, is that that is a binomial distribution. It's a binomial distribution with, let's say, some specific degrees of freedom. So the binomial distribution is written down as follows, where you state the theta raised to the power of k multiplied by 1 minus theta raised to the power of n minus k. And that is how we usually write down the binomial. So that means that if you know how many times heads you've thrown, and you've known you have thrown a certain amount of times, n, then you can actually calculate what the probability is of that instance. And that is actually exactly what we've done when we drew our probability function for throwing 10 times under the null. In that sense, under the null, we assumed the theta to be 0.5, and we calculated for every number of heads, 0 to 10, assuming we throw 10 times, what those associated probabilities are. So in that sense, that was the state of the world, the state of theta, determining the binomial distribution. But what we're doing with Bayesian statistics is we're flipping it around. We're saying, well, given that I throw 2 times out of 10, what are all the theta values possible within that range? So that's what we're doing with Bayesian statistics. And as a prior, I choose one where I set my my k to 25 and my n to 100, and that such a distribution of the likelihood of theta results in this distribution. So what you're actually saying, for all possible values between 0 and 1 of theta, for 25 and 75, if I calculate this for every possible value of theta, the relation between theta and the likelihood here on the y-axis is distributed like this. So these are my initial beliefs. Now the question is, what is the data telling me? So we now have our prior. I've chosen a quite a stubborn prior, but hey, that's me. But now the question is, what does the data tell me? And I threw 2 out of 10 times heads. So that's k being 2 and n being 10. And that's also a binomial distribution. But in that sense, I now want to know what is the likelihood for every possible theta between 1 and 0 for that specific numbers of heads when I throw 10 times. We already determined that the most likely value of theta, given these throws, was 0.2, right? We said, well, if this is your data, then the most likely associated, if this is your data, the most likely associated theta would be 0.2. But if we would have other values of theta, how likely would such a result be for those values of theta? So this is what we think for the most likely one. But what about the rest? And so what we're doing, what we want to do now is essentially make a likelihood function of all the possible thetas that you could have, assuming 2 over 10 to be the state of the world, to be true. So we're going to look at this, and this is the distribution that we find under there. So my initial belief, my stubborn belief is this one, top right. And when I look at the data, we see this. So I think I saw in the chat at one point, so we're not dealing with p-values in Bayesian statistics. No, we're looking at distributions. We determine our hypothesis in terms of a distribution. We're saying, well, I think that it looks like this. And in terms of the data, we're not looking at a probability of finding a specific value of the data or more extreme. No, we're saying, what is the distribution? The likelihood function of our parameter if this data were to be true. So essentially you're saying the data drives the state of the world. And this is such a distribution. So what I've done next is this plot. And what we're seeing here is, based on that distribution of theta, the associated binomial distribution. So we're looking very explicitly of throwing 2 times out of 10. So this is marked blue here. And you see that for a very high value of theta, that is, such a value doesn't occur much. As for having a theta value of 0.2, the most likely one, the highest one, you also see that the associated probability within the binomial distribution is the highest. So what we're doing here is just fixating on just 2 out of 10 and determining, essentially reasoning backwards, what is the likelihood for the value of theta. And you see here a theta of 1, then it's absolutely unlikely that you find such a value. So such a value is actually indicative that we don't find this in when our theta is actually 1 or 0.9 for that matter. Are you seeing this relation?
Yes.
Very good. So now we have our prior belief, we have our data, so we can now update our belief based on the data we found. So we can now calculate our posterior and update our belief based on the likelihood function. So in terms of Bayes' rule, where you say you update your belief, so your prior belief is proportional to the likelihood times the prior, you're saying that you're multiplying your prior belief with the likelihood within given the data, within the data. And to get to this result, you're actually quite literally multiplying distributions. So that is a big step that the Bayesians make, going from the Lego experiment, where you actually have your outcome space. So these are all the possible outcomes that are there, to saying, well, I assume something like this in my prior belief, but now I want to update this. And the step is that these are quite discrete in terms of what is possible. But now we're looking at continuous likelihood functions. One for my prior belief, that's this one, and one for the actual data, which is also a binomial distribution. So you have to understand this, you have to realize that these formulas are actually determine the shape of your distribution. The fact that you have 2 here and 8 here means that if you plug in all the possible values of theta, you get the shape that we've seen previously. So now you are multiplying this distribution with your prior believed distribution. And if you multiply that, which is actually quite easy because you can just add up all the exponentials. We have 25 plus 2 is 27, and if we subtract those two from 10, we have 8 and 75. We land on 83. So my updated belief is this one. And visually, because that's of course more intuitive than looking at formulas, intuitively it looks like this. We have our prior belief here, my personal stubborn prior belief, because I really wanted to hold on to my estimation of the points being skewed to the right with a theta of 0.25. I was quite convinced of myself, and I had quite a small and narrow distribution. But the data spoke otherwise. They said, well, you threw 2 out of 10, and the associated theta distribution, the likelihood distribution here, looks like this. So you thought this, and this was the case. And if I multiply these two, then I will get my posterior belief. So I'm still a bit in the on the good belief, right? My initial thoughts are validated by my updated belief, because, well, it was a bit widespread, but it's still around my 0.25-ish, 0.3 maybe. So I could update my belief based on this graph. Are you following this? Does this make sense?
Yes.
Yes.
I actually find it a bit confusing. If I look at the original Bayesian rule, where it was like P, the probability of A given B and stuff like that, because now you just multiplied something with something else, but you didn't do the dividing part.
No, I did not, and that's the step that's the Bayesians essentially make, right? With the likelihood part, where you had previously the likelihood being defined as this part, the probability of the data given the hypothesis divided by the data. They just go in one step from that to stating, well, this represents my data, and I will operationalize this in a likelihood. So
Okay.
that's absolutely the case, and that's true. So it's a big step, right? From this to that, and
Yeah.
mathematically you can prove that you're somewhat in the that this holds, and I won't bother you with that for this course. But this is absolutely the case. We're making conceptual steps, because what we're saying here is, well, this is my prior belief in terms of a probability of an hypothesis, and we're now stating, well, instead of just having a prior belief as a probability of my hypothesis, I'd now define that as an entire distribution of possible outcome values.
Yeah.
So
Okay.
you're absolutely right. It's a very big step going from such a formula to updating your prior belief.
Yeah.
Can anyone tell me why this is such a wide distribution?
Because we only had 10 throws.
Exactly. So you're seeing essentially your you could have a prior belief that you could where you could increase your certainty in that belief by making your distribution narrower, and in terms of data, you could make your confidence in your data higher by having a higher sample size. And the same holds there.
I have a question.
Of course.
So just assuming that we would have had the exactly opposite prior belief, and we find something as data similar to that one that you actually found in this case here.
Yeah. Would
it then, the result, the posterior, would it be flattened then, or would it peak around 0.5?
So it depends on your prior belief. So if I, for example, had a prior belief that my distribution would be somewhere around here, more to the right, so peaked somewhere here.
I can't see the slide.
Oh, sorry. Yeah. So, for example, if my prior belief would be more to the right, so it would be peaked somewhere around here, then it would, multiplying these distribution would pull your belief to the right. And I think intuitively it would land somewhere in the middle. So it would be pulled indeed more to the right. But for example, if I would have had a flat prior, then it would not just, wouldn't pull it to the right, it would pull it, it would squish it down in all directions.
Okay, so in this case, if you would have the opposite prior, then it wouldn't flatten. It would change the curtices.
Yeah. Yeah.
Okay.
It would pull it more to one direction, but if you would choose a flat prior, it would flatten the curve.
Okay. Perfect.
So it all depends on your prior, and even if you would have a prior that extends out on the side, so it's low at 0.5 and high at 0 and 1. So it's a upside down parabola. Well, you can imagine what this would do with your with your posterior, it would also try to flatten it out, because multiplying those distribution would pull it out, right?
Yeah,
You
thank you.
Yeah?
Thank you very much. Yeah, that explains, yeah.
Okay. So what we're seeing here with multiplying essentially the distributions, it's essentially, visually doing this. It's saying, well, this is my prior belief, this is my data, multiply these two distributions and I get a new distribution, and this is my posterior belief. Now, if you, and that's the updating thing with the Bayesian statistics, right? Because they say, well, if you state that your posteriors of today are your priors for tomorrow, that means that the next day that I do this experiment, this posterior distribution, I will use this posterior distribution as the input, as my prior belief, because I'm updating my belief. If I run the experiment again, throw a number of times heads, and then I can update my belief again, right? So that is what's happening when you update your belief. Now, consider, for example, consider that the true theta in our case would have been, or is, 0.68. Can you imagine that?
Yes.
So my initial belief is totally off, because in reality it's 0.68. And even if I have a theta of 0.68, it sometimes happens that if I throw 2 times out of 10, that I throw 2 times, if I have a theta of 0.68, it sometimes happens that I throw 2 times out of 10. So I have updated my belief, and the data has shown me something that is actually not, it's plausible under a theta of 0.68, but you see here that I'm still way off, right? I still don't have an actual good notion of what's going on in reality. Are you seeing this? Do you understand? Yeah. So we're actually a bit stuck here, because if you approach this Bayesian statistics in the same way that you approach the frequentist statistics, and well, let's phrase it otherwise. If you consider your research, doing one experiment as giving you answers to how reality works, if you do one experiment to see if there's a difference between males and females on whatever, then the frequentist statistics tell you, well, if you find a difference, right, that's highly unlikely if nothing were true. And within the Bayesian statistics, you could still say, well, it's that hypothesis holds or not, but if if both are just a one-time run of the experiment, then both can be off. Your null hypothesis could be off, and you won't have any idea on the alternative. And within Bayesian statistics, you see here that you can still be off.
If I get this correctly now, so one big problem with Bayesian statistics is the external validity, because you can't generalize it if you take one sample basically and then base your probability on that one sample. Because, for example, the coin example, right? Mm-hmm. You have the 2 out of 10, And if you now assume that this is the case for everything, and this is kind of the new probability, I think then that's a big problem, right? That you can't generalize it then, really.
Yeah. So that's a problem, but Bayes solves this in terms of updated belief. But to make that really happen, you do have to update your belief. So I've updated my belief here. It's shifted a bit to the right. But what I'm going to do now is I've written a little program. So bear with me, but try to see what's happening here. Yes. I state my actual theta to be 0.68. And I have, it's a binomial, so I have the numbers of heads and the numbers of the total number that I have for n. So this is not really the number of heads, but it's more like the parameter. Let's not call it parameters. Let's call it degrees of freedom of my distribution. So after updating this thing, I've seen here that my new distribution is theta 1 minus theta 2738. So I'll start with at this point. So what I'm doing here is, well, I'll start with a distribution of 2738, 83, sorry. I'm gonna run 20 experiments. This is a simulation.
The real theta here is referring to the theta of the posterior, right?
No, it's referring to an unknown theta.
Okay.
Which is in reality also unknown. It's just if this is really the data driving factor, then my posterior belief that I had is absolutely off because I thought it was 25. I now updated this based on our single run of the experiment, and it's now, I think, well, let's see, I think 30 or something, somewhere between 25 and 30 here. But in reality, which we of course don't know, but in the simulation I can do this. I say it's 68. Totally arbitrary.
So that's what we actually don't know, this one.
Yeah, exactly.
Okay, I see.
So what we're doing now is we're taking a sample with sample size n of somewhere in between 30 and 100. So this means that I'm going to do 20 replications of this study with somewhere between 30 and 100 people. So it also shows you that within Bayesian statistics, you don't have to replicate the exact same way as you would have to with frequentist statistics. Now we can now say, well, I can mix and match. And what we're doing is we're sampling a random set of zeros and ones where we set our sample size that we just determined up here, and we give it a real theta. So the numbers of zeros and 1 are produced by the data driving factor, by the fact that we choose our 0.68. And what I'm doing then is I'm determining my new k and my new n, because if I multiply those distributions, I'm actually adding up those k's and those n's by the new numbers of heads, the new total sample size. And now I'm plotting my likelihood function, my posterior and my prior distribution. So it does this 20 times repeatedly, and it will update my posterior based on every iteration.
So can you, to speak in middle school math terms, can you say that it's kind of similar to having the lottery, and you pull, like you basically don't put it back, like after you drew a lottery ball, exactly. You don't put it back, so then the likelihood change, the probability changes with every sample, and you account for that.
No, I give it a predefined theta, a predefined parameter of 0.68 for everyone. But I update my belief. So I start here. This is a loop, by the way. So it starts every time it flips back to the left. And you see that going from my prior belief and updating this in the posterior, putting the posterior back in my prior belief and doing another sample, it shifts my posterior distribution to the right, to where the actual parameter value is. Do you see that?
Yes. So basically, should we assume that the 0.68 is the actual value, and that the more that we test, we get closer to that value every single time?
Exactly. That's exactly what we're seeing here. And the thing here is that we do have to test multiple times. To be sure, you have to replicate and redo your analysis, use your prior knowledge to update your beliefs, and then it will converge to the point where it actually is.
Okay.
Are you seeing this? Very good. Very good. But this is not really. We've talked about the null hypothesis testing, right? Where we said if we want to have a good notion of what our alternative distribution looks like, then we have to do our experiment multiple times, and we have to report multiple effect sizes, so we can use those effect sizes to hone in on where our alternative distribution actually is, or where our mu of our alternative distribution is. So in essence, and I think this is the take-home message, that Bayesian statistics handles this elegantly, but if you do the frequentist analysis properly and also there replicate, then you can also get to your alternative distribution. You can also hone in on the actual parameter value. So the take-home message is that either methods work, but you have to replicate, because only learning from your prior knowledge you will get a better sense of what is actually going on. For Bayes, the take-home message is the Bayesians quantify uncertainty through distributions. We've seen that. If you draw a tighter distribution, you have a better, you are more confident. The more big such a distribution is, the lower the uncertainty. And incoming information continually updates your knowledge. So today's priors are tomorrow's. So today's posteriors are tomorrow's priors in updating your belief. We're not done yet, because calculating, estimating your parameter is one thing, and it's nice to have a good understanding or being certain about your parameter value. But sometimes you actually want to compare. So when we looked at the Lego example, we're comparing our hypothesis, our alternative hypothesis, in terms of drawing such a distribution to not having that distribution. So sometimes you want to compare competing hypotheses. So you could also do this hypothesis testing within the Bayesian framework. And there is a special case within that Bayesian framework where you can actually state that you would want to test two competing hypotheses to essentially a null state. And this is not really hard to imagine, because you can see in such a distribution, both for these, that the actual null state would be where the theta would be exactly 0.5. So within, oh sorry, yeah. So within all the possible space for theta, the null state would be the state where the theta would be 0.5 within such a distribution. So if you look at Bayesian hypothesis testing, then the null hypothesis testing would initially be an invariant state, an invariant law, where you would, for example, state what the specific theta would be. So the null state for our coin experiment would say that our theta is 0.5 and nothing else. So you could imagine a distribution being totally flat and only at 0.5 being peaked and then being flat again. So that would be the null state. Whereas our alternative states, well, we've just drew a few of those alternative states of our hypothesis that we could have. So in terms of comparing hypotheses, you could, and this is associated as the Bayes factor, look at the ratio between such two hypotheses. So updating your prior belief based on the likelihood to get to your posterior belief, this would hold for your alternative hypothesis, but the same would hold for an H0 hypothesis. And if you look at the ratio, that ratio would be high if the above one, it has a higher value than the lower one. That makes sense, right? To be a ratio, just like a signal to noise ratio. This is one hypothesis pitted against the other hypothesis. And this is something that is computationally, a bit of a challenge, but you could also state that such a Bayes factor, so you could approach that ratio within a Bayes factor where you actually look at the state of null of your parameter for your prior distribution compared to your posterior distribution. And that sounds a bit strange, but what you're actually doing is comparing those two distributions in the sense of what is the ratio between these two at the specific point of theta being 0.5. So let's see. We're gonna do get this shiny app to work here, and we're gonna use this one. So what we're seeing is the Bayes factor for let's see, the Bayes factor for an 1, 0, meaning we have a Bayes factor in favor of an alternative 1 hypothesis pitted against the null hypothesis. And what we're seeing here is a flat prior, and we're seeing at the other side the opposite, so the Bayes factor in favor of the null versus the alternative. And we see on our x-axis all the possible theta values. So it can be between 0 or 1. So if I throw 1 times heads and 1 times tails, you see what you're seeing in the red line is the posterior distribution. So updating my belief based on my flat prior, updating my belief will yield me the posterior distribution. And in the light of new data, you can see the alternative distribution, the posterior distribution change over time. So you can see by this example that Bayesian analysis also allows you to just add more data where that in frequentist statistics would be absolutely not done. But even in this case, for example, where we've updated our beliefs, where we have a parameter estimation that would shift the parameter value up, doing null hypothesis testing would state, well, how likely is 0.5, assuming the null to be true, under our alternative distribution, not alternative, the posterior distribution, after updating my belief, versus my initial prior belief. So this special value of 0.5, which would represent the null, is, well, even if this distribution changes, the ratio of 0.5 for the posterior distribution or for the prior distribution is equal. You see, these values are actually, well, the same. So my update, even if I updated my belief, I could still see here that testing a null assumption, in contrary to what the name and Pearson paradigm does cannot just say something about just your null assumption, but it can compare to what your prior beliefs are for that specific value of the null. But if we see that even if it changes, well, I get a base factor now for our alternative that goes up quite a bit. So the ratio, again, so it's not the height, but it's the ratio, is now in favor of my alternative distribution versus the null distribution. So you can see that you can test essentially your very specific null situation to the rest, and that is what we're actually saying with the base factor.
Can I ask a question?
Yeah, sure.
So I was like, how does this work in real work? Because right now it looks like we're just taking a wild guess for theta. But how can you like scientifically support your belief?
Well, it's a continuous scale. So that base factor indicates your the likelihood of your updated belief compared to your previous belief, or compared to especially at the null state. So
it doesn't really matter where you start; it's just like a starting point.
Yeah, but okay, that's the entire debate. Well, where you start determines a lot, and that is where the Bayesians clash with the frequentists, because the frequentists say, well, you can start anywhere in your favor.
Yeah,
but
right.
the thing to take home is that this base factor gives essentially the ratio of your updated beliefs compared to your prior at the null state. Harold Jeffries indicated some thresholds to state that your evidence is just anecdotal or moderate, and only if you have very strong evidence for one alternative, for one prior, then you really need to have very high values of this base factor to pitch you in that direction. Okay, I'm wrapping up. So the advantages are, it provides such a base factor for testing the specific null, provides a continuous degree of evidence without requiring an all or nothing decision, as you have in frequentist statistics. It's either you reject the null or you don't reject the null. Now, with the base factor, you can say, well, I believe more in this hypothesis than I believe in that hypothesis. It allows for monitoring during data collection, so you can accumulate evidence for your hypothesis, or against, for that matter. And it differentiates between the data supported under the under a null assumption and the data and data that is non-informative. So, for example, we've seen the flat prior that's non-informative, but it can even be that if you have a state which is not informative, your updated prior belief at the assumption of 0.5 is even as informative under the posterior distribution as it is on your prior distribution. So it pits those two against each other. Base factor of 1 means evidence for the alternative is the same as your evidence for your null. A base factor of 3 means I have more evidence for my alternative than I have for my null. And the base factor going down 1/3 means I have less evidence for my alternative than I have for the null. So you can have a notion on how such a base factor is essentially what it indicates, the height of the base factor. Bayesian statistics can be done by JASP, which is developed at our methods department of our of the psychology department. And if you're interested, you can get in touch with EJ, who will have a debate with Danny Borsboom as the frequencies next week. And on that note, I will actually end this lecture because we're 5 minutes late. I'm sorry for that. I will stick around for questions, and otherwise I wish you good luck with the weekly assignment again. I really look forward to the debate because I think it's going to be wonderful again. And I also wish you the best of luck with preparing for the exam. Bye, everyone.
Thank you very much.
Bye.
Bye.
Thank you.
Bye.
Bye.